This is part 7 of an ongoing series about the origin of the elements. So far, we've been building elements by fusion. We start with hydrogen, we make helium, and then under increasingly extreme conditions, we can build progressively heavier nuclei. But there's a problem, as we saw when we talked about binding energy. Fusion only releases energy while we're moving toward the ion peak. Once you get into the ion region, sticking nuclei together no longer gives the star an energy payoff. In fact, to keep fusing towards heavier nuclei, you have to put energy in. So ordinary stellar fusion has basically run out of steam. But the periodic table obviously doesn't stop at iron. We have copper and silver and gold, we have lead, we even have uranium with 92 protons. So we have a new problem. If we can't make these elements by simply fusing charged nuclei together, how do we make them? And that's actually a big enough story that I'm going to split it into the next 3 short episodes in our Origin of Elements series. In this episode, we'll look at the basic nuclear physics, how we use neutron capture to build heavier nuclei, and why that gives us 2 very different processes, the S process and the R process. In the next episode, we'll look at the fingerprints those processes leave behind and the evidence for where the S process actually happens. And in the third, we'll tackle the remaining mystery, where does the R process happen? But first, we need to solve our original problem. If sticking nuclei together has become increasingly difficult, perhaps we need to stop trying to add protons. So we need another way to build heavy nuclei. Our problem with fusion is charge. If we try to add another proton, I'm trying to push positive charge towards positive charge. The Coulomb barrier gets increasingly difficult to overcome as the nuclei get larger. So instead, let's add something that has mass but doesn't have charge, a neutron. Because a neutron is electrically neutral, there is no Coulomb barrier to neutron capture. We don't need the extreme temperatures required to force 2 positively charged nuclei together. So this looks promising. Take a nucleus, throw a neutron at it, and make a heavier nucleus. Except if I add a neutron, I've changed the mass, I've changed the isotope, but I haven't changed the element. If I start with iron and add a neutron, I still have iron. So neutron capture gives us part of the solution. Now we need some way to change a neutron into a proton. Here's our starting nucleus right here. And here we have a neutron that we're trying to add to it. So this nucleus has a mass of A and an atomic number of Z. As we add the neutron, it captures it, and now it's got extra mass, A plus 1, but it still has the same number of protons, it's still the same element. It also gets some energy, so it gives some off as a gamma ray. But now we've got something that is not stable, and so it's going to eject particles to make itself more stable. So in this case, we're going through beta decay. So we've gained a neutron, but now that neutron is going to eject a beta particle, which is an electron, and a neutrino, and what we're going to get is a proton instead of a neutron. So now what we've got is we've gone from here, where we're still this same element here, we've decayed by converting a neutron to a proton, and now we've got still the same mass, but we've changed and we've got Z plus 1. We've added a proton. And it will be a little bit energized through that process, and so it has to lose a little bit more energy until it's finally at its final stage. So by adding a neutron, we can convert something from atomic mass A and atomic number Z to atomic mass A plus 1 and atomic number Z plus 1. This is basically summarized down here, where you can see neutron capture. A goes to A plus 1, and so we've got the same element, Z is unchanged, but then the beta decay means that the A is unchanged, but the Z goes to Z plus 1. Neutron capture changes the isotope, beta decay changes the element. But now there's an important question. Once the nucleus has captured a neutron, does it have time to beta decay, or does it capture another neutron first? The answer depends on which process happens faster. So we have 2 processes that can happen in a neutron-rich nucleus. It can undergo beta decay, or it can gain another neutron. If it undergoes beta decay, then it's going to increase its atomic number by 1. It's going to change what element it is. If it adds a neutron, it's just in changing its mass. And this basically determines what pathway isotopes will be formed during the process of neutron capture and beta decay. So what happens depends on the relative rates of these two processes, neutron capture versus beta decay. And that fundamentally is a difference between the two major ways that neutron capture builds heavy elements. Rather unimaginatively, we call them the slow neutron capture process and rapid neutron capture process, the S process and the R process. So we've established that we have two things competing to happen. A nucleus can capture another neutron, or it can beta decay. Let's start with the slower case, the S process. So our nucleus captures a neutron, and then there's time for it to beta decay before another neutron is captured. Remember what beta decay does. A neutron becomes a proton, so the atomic number increases by 1, and we've moved to a new element. Then that nucleus might capture another neutron, and if it becomes unstable, there's again time for it to beta decay. So the sequence looks something like this. Capture neutron, wait, beta decay. Capture neutron, wait, beta decay, and so on. The word slow doesn't mean that the neutron itself is moving slowly. It means that neutron capture occurs slowly compared to the timescale for beta decay. The distinction is important. The nucleus, therefore, doesn't get enormously neutron-rich. It generally has time to beta decay back towards stability before it captures the next neutron. So the S process builds heavier and heavier nuclei while staying relatively close to the region of nuclear stability. And we'll come back shortly to where in the universe we actually find conditions that allow this to happen. Now let's change the conditions. Suppose that instead that our nucleus is surrounded by an enormous number of neutrons. It captures one neutron, but before it has time to beta decay, another neutron arrives, and another, and another. And so the sequence looks something like this. Capture, 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 and it keeps going until eventually it's so unstable that it can beta decay. This is the rapid neutron capture process, or R process. Again, rapid refers to the rate of neutron capture relative to beta decay. The captures are happening so quickly that the nucleus gets pushed further and further away from stability, becoming extremely neutron-rich. Eventually, though, the supply of neutrons no longer beats beta decay because the nucleus is so unstable. Now the race changes. Neutron capture is no longer winning, and these neutron-rich nuclei undergo beta decay. And not just necessarily once. They may go through a whole sequence of beta decays, converting neutrons into protons and moving back towards stability. So the S process and R process use exactly the same basic ingredients, neutron capture and beta decay. The difference is in the timing. In the S process, beta decay can happen between neutron captures. In the R process, neutron capture happens faster than beta decay. And that difference sends the nuclei along very different paths. To understand those paths, we need to look at which combinations of protons and neutrons actually make stable nuclei. We've said several times now that a nucleus can become too neutron-rich to be stable. So what exactly do we mean by this? Not every possible combination of protons and neutrons becomes stable. If we plot the number of protons against the number of neutrons, the stable nuclei occupy a relatively narrow range. Here it's the part in blue. We call this the valley of stability. No nuclei here are plotted in green, and these are the ones that are not stable. They are radioactive. One warning about these isotope maps: there isn't a universal convention for which axis is which. So whereas this case I have protons on the horizontal and neutrons on the vertical, some plots will put the neutrons on the horizontal and the protons on the vertical, and we'll see both examples during this presentation, so please check the axes. Now for the lightest elements, the stable nuclei tend to have roughly similar numbers of protons and neutrons. That ratio, having equal number of protons and neutrons, is indicated by this black line. But as the nuclei get heavier, that changes. We're putting more and more positively charged protons into the nucleus, and those protons repel one another electrically. The strong nuclear force holds the nucleus together, but it acts only over a short distance. Heavier stable nuclei need proportionally more neutrons than protons. The neutrons contribute to the nuclear binding without adding any electrical charge. So as we move towards heavier nuclei, the value of stability bends away from the simple one-to-one relationship between neutrons and protons. Now, nuclei can also exist outside this valley, that's the green area, but they're unstable. If a nucleus has too many neutrons, beta decay can move it back towards stability by converting a neutron to a proton. And that's exactly the process we've been talking about. Now think back to our two neutron capture processes. In the S process, there is generally time for beta decay between neutron captures. So the path stays relatively close to the value of stability. But in the R process, it can add neutrons faster than the beta can decay. And so what do we think is going to happen? It drives the nuclei up in neutrons, so in this direction on this graph, and we end up with something that's very unstable with lots and lots of neutrons. And that's going to have some very interesting consequences. Now let's look at a map of real isotope. It looks a little complicated, but we're going to build up to it. On the vertical axis on this one, we have the number of protons, and on the horizontal axis, we have the number of neutrons. Moving up takes us to a different element. Moving to the right takes us to a different isotope. Let's start with neutron capture. If I start here with sulfur, and I add one neutron, I still have sulfur, but N is increased by 1, I have a mass of 33. In this case, this is a stable nucleus. Blue are stable. So it doesn't change much. So then I can add another, and I still have a stable nucleus. So then I can add another. And when I get to here, I get to an unstable nucleus. And under the S process, we're going to have time for it to decay. Another example of this would be here with phosphorus, where it's stable at 31 nucleons, but as we add another neutron, it becomes unstable, and then that neutron can become a proton, and we get sulfur. Neutron capture pushes us to the right, and beta decay pushes us up and to the left. Now we're going to see a bit more of this map. So here you can see this is a more complicated version of this. And you can see here that when we got to sulfur 35, which is unstable, it would beta decay to chlorine. So we can actually trace the path of elements through a path like this that is following all of the different possible decays. In this case, it actually has some extra decays, which I'm not going to get into. Now remember, we have two competing clocks. So if the beta decay has time to occur between neutron captures, we're going to follow one kind of path. But if the neutron capture keeps winning the race, we're going to follow a different path. Well, let's repeat this sulfur. We've got sulfur 32 here. We add a neutron, it's still stable. We add a neutron, it's still stable. We add a neutron, it's not stable. It will beta decay and give us chlorine 35. But if we have more neutrons coming faster than it can decay, it will then move to sulfur 36, which is stable. And then you can add another one, and now it's unstable, and that will decay, and that will give you chlorine 37. So you'll get different isotopes as well as different elements, depending on whether you're injecting neutrons very rapidly or very slowly. So let's make this concrete and follow a real set of nuclei on a mini map. Suppose that we've got iron 56. This is our most stable element. We're adding a neutron. If we add a neutron, we get iron 57, which is still neutral. And then we add another neutron, and we get iron 58, which is still neutral. And then we add another neutron, and now it's not stable. But because we've reached an unstable isotope, and we're looking at the slow neutron capture process, there's time for beta decay to happen. And so now with beta decay, what's going to happen is we will have an electron injected, that's a beta particle, and we will get a new element. And this time we're going to get cobalt. It has the same mass, but we've now got an extra proton. It is cobalt 59. So we lose one neutron, we gain one proton, the mass number stays the same, but the atomic number shifts. So we've made a new element. We didn't fuse iron with another charged nucleus. We added a neutron, and then beta decay changed one of those neutrons to a proton. We made new stuff. Let's look at this process in a little bit more detail. Again, we've got iron 56, 57, 58 is all stable, but as we move to 59, it's not stable. If we're working through the slow process, it should have time to decay and go to cobalt. But now we've got our cobalt and it's stable, we can add another neutron, and now it's cobalt 60. But that's unstable, and that will go to nickel 60. But if we're in the fast process, we'll get to iron 59, but we can add another neutron before it decays, and another. And so now we're at iron 61, and that's going to decay. It's still going to first go through cobalt, because that's what happens when you change a neutron to a proton, but that's also unstable, and that's going to make nickel 61. And you can see how this just keeps on going, and you can make all sorts of different elements. So let's go back to that more complicated isotope map. We just followed one real example from iron to cobalt, but there's nothing special about that particular step. We can repeat the same process over and over. Before we do that, let's remind ourselves where the valley of stability is. So here we've got that little map that we already saw. Just a reminder here, this has the axes transposed, so it's got protons on this side and neutrons on this side. I'm sorry about that. I want us to look at where this piece fits on the map of stability. So here we've got silicon, that's 14 protons and 14 neutrons. Here's sulfur 32, 16 protons, 16 neutrons. Here's calcium 40. And so what we've got is something that is basically falling in this zone here, in the sort of 10 to 20-ish on each axis. And so we're right down here. The blue here that is stable is also the blue here on our complicated isotope map. And the green here is also unstable. And so what we're seeing here is that a zoom into this little piece here where we're seeing the details of the valley of stability. Let's start with the S process. Remember, neutron capture is slow compared to beta decay. So we capture a neutron, so we're going to start with our sulfur again. We move to the right. We might capture another one if that's stable. And we might capture another one if that one's stable. But now we reach something that is unstable, and the time scale for beta decay is faster than another neutron can come along. So now it's going to decay, and it's going to become stable again. So the beta decay is taking us back to stability. Now we can add another neutron, but it will beta decay again back to stability. So if we look at the path we've made, we tend to stay very, very close to the blue part. We're going to be having things that are very much close to the path of stability. The S process tends to hog the valley of stability. It wanders away as neutrons are captured, but beta decay helps bring it back towards stability before it can get very far. Now, let's run this again, but change one thing. Suppose the neutron capture is enormously high. So now we're capturing a neutron and capturing a neutron, and we can keep going. But we get to here, and the neutrons come faster than it can decay, so it goes to the next one. Now that one's stable, so it captures another one. And actually it can keep going. It could be sulfur 38, sulfur 39, and so on. So instead of zigzagging along the valley of stability, we're driving the nucleus further and further out into the neutron-rich side. Eventually, though, that intense supply of neutron ends, or something else happens to make it difficult to add the neutrons, and we're left with an extremely rich nucleus that's nowhere near stability. So what's this atom going to do? It's going to beta decay. So now what we get is that we have something that's all the way out here, and it's going to start beta decaying, and it's going to beta decay up a path in the direction of the valley of stability. So now we can see the fundamental difference between the two processes. The S process stays relatively close to the valley of stability because beta decay can occur between neutron captures. The R process races far out into neutron-rich territory because neutron capture happens much faster than beta decay. And then when the rapid neutron capture ends, those neutron-rich products decay back towards stability. Here's something to think about. If these two processes take such different routes across the nuclear landscape, they don't necessarily make the same isotopes. We've solved our original problem. We now have two ways of building nuclei heavier than iron without having to overcome the Coulomb barrier. That's the S process and the R process. But we've also created two new questions. Where in the universe do these processes actually happen? And how do we know that any of this is really happening? Those are the questions we will tackle in our next episode.